In this section, I'm going to use the buck-boost converter as a typical example to show you how can we establish the AC equivalent circuit model of power converters. So actually, we have multiple methods to model the converter. So today we are going to introduce the first one, which is called the basic AC modeling. So first, let me plot the schematic of the buck-boost topology. We have the input source as VGT and a switch network. So this is a single pole double throw switch, and we have an inductor here, L, and the filtering capacitor and the load resistor. So here is the output voltage. Note that we denote the positive sign on the top. So we know that the buck-boost is an inverting topology, so it means that the output voltage should have a negative value if we denote the upper side as the positive. And in order to facilitate analysis, we need to define those critical signal positive directions. First will be the input current. Second one is the inductor voltage. Third one is inductor current. And the fourth one is the capacitor current. We denote this as the positive polarity for capacitor current. Okay, so we can do the mode analysis for continuous connection mode. As we previously mentioned, in CCM, we have two operation modes. First one is the mode 1. Mode 1 occurs from 0 to DTS. So here we use the lowercase d, meaning to indicate that this d is the full signal, which includes the DC bias and small signal perturbations. So in mode 1, we can plot the equivalent circuit for buck-boost converter. So the switch is triggered to position 1, meaning that the input source is applied to the inductor directly. And on the output port, we have capacitor provide power to the load resistor. So for the mode 1, we can express the inductor voltage accordingly. So VLT. First, based on the nature for the inductor, the V voltage across it equals to L times di over dt. Secondly, based on the KVL in this loop, the voltage across the inductor equals to the input voltage. And approximately, by ignoring the frequency components variations, so we can equal this to be average value for input voltage over one switching period. And second equation will be inductor current. So by its nature, it equals to C times dV over dt. And based on KCL principle, this current will be equals to minus the load current, right, which is voltage over resistance. And approximately by ignoring the small signal ripples. So this equals to the average value of output voltage over one switching period. Thirdly will be the input current. This equals to the inductor current. And also we can do the small ripple approximation. This equals to average over one switching period. Correspondingly, we can plot the critical waveforms. Note that this critical waveform applies both to steady state and perturbed system, meaning that this can be used for dynamic analysis. So we care about the three signals, right? So we plot them one by one. First one will be inductor voltage, VL, in time domain. Second one is capacitor current, ICT, in time domain. Third one will be input current, IGT, in time domain. So basically there are two operation modes, right? First one is from 0 to DTS. Second one is from DTS to TS. First, we fill the mode 1 part. In mode 1, inductor voltage equals to like this. So its average level equals to average input voltage. And the capacitor current will also have such a shape. The average equals to average output voltage divided by R. Because buck boost is an inverting topology, so this output voltage is a negative number. So negative means the positive. The capacitor current is positive. And for the input current, it equals to the inductor current, right? Inductor current will have a slope. So here is the average value. So average value equals to the average inductor current over one switching period. All right. Next, let's look at what happens in operation mode 2. Mode 2 happens from DTS to TS. So in mode 2, the switch is pushed to position 2, but the input source is opened. So we can plot its equivalent circuit. Here is the input source. Here is L. C, R. So originally the current of inductor flowed downside. By pushing the switch to position 2, this current will continue to flow, right? Meaning that there will be a current pulse like this. The inductor current charges the capacitor and provide current to the load. And correspondingly, we can write those three equations. The first one will be the inductor voltage equals to L di over dt. So based on KVL, right, this voltage in mode 2 equals to output voltage. And the small ripple approximation tells us that it equals to the average output voltage over one switching period. And the second one is the capacitor current, C dV over dt equals to, based on KCL, right? The capacitor current in mode 2 equals to, because this current plus this current plus this current equals 0. So the capacitor current equals to negative IL minus the resistor current. So small ripple approximation tells us that minus average inductor current over one switching period minus average output voltage over one switching period. And the third one will be the input current, which is simple because input is opened, so the input current equals to 0. All right, so next let's try to do the average over one switching period. So average over Ts. First will be inductor voltage. So the average inductor voltage over one switching period equals to L the average inductor current over dt. That is the nature for inductor, right? And this will be equals to the average of inductor voltage considering mode 1 and mode 2. So the the figure will be more straightforward. So let's try to make up the mode 2 parts. So for the mode 2, from dTs to Ts, the inductor voltage equals to this quantity, which is a negative number. So we'll have the mode 2 curve like this. And for capacitor current, similarly, equals to this quantity, which is also a negative number. And for input current equals to 0. Okay, so now we have completed the 3 critical waveforms. And it's more straightforward to analyze the average value based on the graphical illustration. So for the inductor voltage average, so it equals to D times level of mode 1 plus D prime times level of mode 2. So equals to D mode 1 and mode 2 counts D prime parts. So where D prime equals to the complementary of D. So equals to mode 1 part plus D prime mode 2 parts here. And secondly is the capacitor average current equals to C times D average voltage of cross capacitor over dt. This average current can also be straightforwardly observed by the graphical illustration here, right? So equals to the positive area minus negative area divided by the period, right? So equals to D part this value plus d prime part this value, we can see that both of them contains v over r term, so they can be combined. So the leading result will have v over r term. And for this one only exists in mode 2, so this will be minus d prime t average inductor current. And the third one will be average input current, which is simple to analyze, right? Just d times the level of mode 1. So that is the 3 critical equations to describe the buck boost operation. And next, let's erase the whiteboard. Okay, I have erased the blackboard, and one more thing is that I moved the equations here to the left-hand side. Okay, now the next step is we can do the perturb and linearize this group of critical equations for buck boost converter. So perturb and linearize. We know that at steady state, the circuit should be operating at its quiescent operating point at steady state. We have quiescent operating point. So which specifies the DC relationship of those critical quantities. For the buck boost topology, we know that at steady state, the output voltage, we use the capital letter to indicate this is the DC quantity, equals to minus d over d prime input voltage. And we have the input, the inductor current equals to minus v over d prime r. And the input current equals to d times r. So those are what we can obtain by the DC modeling method which we learned previously. And those 3 are the functions for buck boost topology. And I'd like to reiterate the illustration of the signal. So we know that we have the real world is full signal. And the full signal can be decoded into 2 parts. One part is the quiescent value. And second part will be the small signal AC variation. So we usually refer this small signal perturbation as the perturbation. So correspondingly, we can represent those average signal by the DC part and perturbations. So we have a group of signals. We list them one by one. First will be the average input voltage over one switching period. Vg Ts. Based on this principle, this can be decoded into two parts. The first part is capital V, the DC quiescent value. Second part is the small signal. Small signal, we use a cap to denote that this is small signal. And similarly, we can do this for duty cycle equals to D plus D cap T. And the inductor current average equals to quiescent value plus small signal perturbation. And also the output voltage equals to quiescent value plus small signal voltage. And also the input current so the quiescent value is capital Ig plus small signal. So we have fully represented those 5 critical parameters. And next step is we insert the perturbed signal into the equation 1, the inductor voltage equation. So insert the perturbation into inductor equation. Let's see what happens. The left-hand side will be L di over dt. So I is this value, right? So equals L times d I plus small signal over dt. So which correspond to this part. Right hand side equals D, right? D equals to quiescent plus small signal D. And Vg is this part. This part, d prime t, we know that d equals to 1 minus d prime, right? So d prime t will be equals to d prime minus small signal d. V is here. That is the perturbed inductor equation. Then we can expand this equation. So left-hand side, we can expand this by breaking the bracket. So left-hand side will be L di over dt plus L di cap over dt. So this part will be equal to 0 because I is DC quantity, which means that it doesn't vary with time. So this can be cancelled as equals to 0. On the right-hand side, we first write the DC terms, right? So D times Vg plus D prime V. So this is the DC terms. Remember, for buck boost topology, this combination equals to 0, right? Also equals to 0. So this can be cancelled. or eliminate it. And second part will be the first order AC term. So we have, for example, D times Vg. We only have one small signal items, that is first order. And similarly, we have D prime B cap plus Vg minus V D cap. So those are called first order AC terms. And next we have the second order terms, right? So basically we have the D times V or D times V, right? So those are D cap Vg minus V. So we call this as second order AC terms. Those are first order AC terms. So actually, if we look at this resulting equation, we can see that these terms equals to 0 can be eliminated. And the second order AC terms means the product of two small signal quantity. Usually, we know that the AC variations are much smaller than the DC quiescent values. That is why we call it a small signal. The second order AC terms means that we have the product of two small signal quantities. So those should be much smaller than the first order AC terms. So in order to simplify an analysis, we can also ignore the second order AC terms and only keep the first order AC terms. So we can further use it to establish the circuit model. Okay, now let's erase the blackboard. All right, we have erased the blackboard. Now let's literally summarize what we did for the perturb and linearize. So basically, first we can say that the DC items for the perturbed equation can cancel on both sides. And secondly, the second order AC terms can be ignored. And this is mainly because the second order terms are much smaller than the first order AC terms. So that we can have only the first order AC terms left. Only first AC terms. By doing this, we can claim that we have obtained the linearized inductor equivalent. So I like to copy the equation we obtained to the right-hand side. Basically, the inductor equation is like L d I cap over dt. So this quantity equals to d times input voltage cap plus d prime times output voltage small signal plus Vg minus V times controlling small signal. And similarly, we can also do this to the capacitors. So we can do the perturb and linearize to the capacitor equation. I will not repeat the detailed procedure. I will only give you the result. So by doing the perturbation, the capacitor equation becomes like CD voltage plus small signal voltage over dt. And right-hand side is minus d prime minus d cap t times the current, the DC current plus small signal inductor current minus V over V plus small signal V over resistance. We can do the 1, 2, 3 by only keeping the first order AC terms. So the capacitor equation will be represented like this. So C times D V over dt equals to minus d prime I cap t. We only keep the first order AC terms, right? So the I times d prime minus. Next part is d prime, d cap times I. And the last one will be minus V over R, right? And the last one is the input current equation. Which is relatively simple. So left-hand side is input current, full signal, right? DC quiescent plus small signal. And right-hand side, D plus D cap times the inductor current, which is DC plus small signal AC. And again, we can step 1, 2, 3 linearize it, keeping only the first order AC terms. So for the input current equation, we'll have D times plus I D cap T. Okay, the following step is we try to utilize those three linearized equations to establish the equivalence circuit model. So we can process them one by one. So first we look at this input equation. So based on the input equation, we can establish the equivalent circuit model on the input side. So input side, we have a small signal AC source, VG cap. Right? And this will be a controlled source, right? Controlled current source. This will be a independent source controlling by external signal. So we can use two current sources to represent them. So this is ID, right? And this one is a controlled source. So this should be current controlled current source. The controlling coefficient is D. Okay. Next, let's look at inductor equation. Similarly, we can construct a circuit to describe this inductor equation. So first, we look at this part. This is a voltage-controlled voltage source. Controlling voltage is on the input port. So we plot this part in adjacent with the input port. So the D times Vg okay. And next we have the L didt, which will be a inductor behavior, whose inductance is L. And next we have this one can be modeled by a voltage source, independent voltage source, because its controlling signal is external. So this can be modeled by an independent voltage source. And next will be this one. This is a voltage-controlled voltage source. Whose value is D prime V cap. Since this is output voltage, so we put this block in adjacent to the output port. And last one will be the capacitor equation. So based on the capacitor equation, we can make up the output port equivalent circuit. So here, right, this will be a current-controlled current source. And it's D prime I cap. Okay, and here is an independent current source, right? Whose value is I D cap. And this will be a capacitor behavior whose capacitance is C. And this is a resistor behavior whose resistance is R. And also we denote the small signal output voltage, V cap. That is the linearized equivalent circuit, right? So next we can go further to try to simplify them. We can circle two parts, right? Here, this circle, if we observe those two control sources, we can see that they have the same controlling coefficient as D. So basically this means that this can be equivalent to a AC resistor behavior. So let me plot the simplified model. AC transformer behavior, okay. So the coupling point is on the same side. But this is not the physical transformer. So we do not plot the common core. Instead, we use a waveline here to show that this is a AC model, right? AC transformer model. The turns ratio is like 1 to D. If you compare them, you will find them they have the same electric behaviors. And on the output port, similar, right? We have a pair of control sources. They have the same controlling coefficient, which is D prime. So similarly as that one, we can use a transformer to model it. But the coupling points are opposite, right? Opposite. And similarly, this indicates that it's AC model transformer. The turns ratio equals to D prime over 1. So if you compare them, you will find they are electrically equivalent. And we copy the rest part. So this is L, this is VG, this is IG. So till now, we can claim that we have established the small signal AC model for buck-boost topology utilizing the basic AC modeling method. Okay, till now we have derived the AC equivalent circuit model for buck-boost topology. We can understand that by doing the switching cycle averaging, and also by introducing the small signal perturbations and by doing the linearization, we can obtain the correspondingly circuit and equivalent circuit model. Similarly, we can also extend this basic AC modeling method to the other topologies. So if you are interested, you can do this after this class to the other pulse width modulated converters.